Okay, so we've seen that cars that drive along the ground use most of their energy overcoming drag and wind resistance, and they're actually extremely efficient. There's not much room for huge improvements there. But terrestrial cars have a big problem: congestion. It's very hard in a big city to get enough cars down the roads to actually overcome traffic jams and get everyone where they want to go in a timely manner. Average travel speeds in cities like London and Paris have not improved in a century, simply because every time a better car comes along, more people buy them, they get more congested, and you end up sitting in traffic jams. But there is a possible solution to this. Imagine we could have flying cars. A car that could take off from your driveway and go wherever you like. This would eliminate congestion at once because you wouldn't need intersections. You can have cars flying over and under each other. You can have streams of cars 20, 30 deep. So congestion's gone away. It would be the perfect solution. Everyone can get anywhere they want without problems. You could then get rid of all the roads. You could replace them with parks or more housing or something. So if we could have practical flying cars, it would completely transform our cities. But we don't have practical flying cars. Why not? Is there a really fundamental limit, or is it just that our engineers haven't been clever enough yet? Well, let's try and investigate the physics of flying cars in the same sort of way that we investigated the physics of ground cars. Okay, so what's our model here? Let's say we have a flying car, as in many, many science fiction movies. How's it going to use energy? Well, there's not going to be any rolling resistance because it doesn't drive along the ground, so that's good. Drag, wind resistance? Yes, there will be drag. If the car is the same sort of size as a terrestrial car and travelling at the same sort of speed, then that'll be about the same. So it's about a few by 10 to the 8 joules. However, there are a couple of complications in terms of drag for a flying car. One is that you might expect a flying car to go much faster. You wouldn't be limited by having to turn corners and stop at traffic lights and so on. And remember that the drag force went as v squared, proportional to v squared, so that could actually drastically increase the amount of energy needed if you go faster. On the other hand, you could in principle go higher. The atmosphere gets thinner as you go up, so if you go to very high altitude above most of the atmosphere, you need to pressurize cars so you don't pass out from oxygen starvation up there, then that could reduce the drag. So there's a few complications about drag. But then, what else are we going to need? Starting and stopping will be about the same as it was for our ground car, so probably negligible in comparison to things like drag. But how much energy does it need to fly? Is there some equation saying if you want to fly a particular distance at a particular speed, it'll take a certain amount of energy? Well, no, there isn't an equation like that. Why not? Well, because flying is actually many different things. So first of all, you've got to take your object up to whatever its cruising altitude is. And that's just going to be like going up a hill, so it's going to be potential energy mgh. But how about staying up there, hovering in the air or cruising along? The cruising along you have to overcome drag, which we talked about, but what energy does it take just to stay hovering in the air? Well, it doesn't really have to take any energy at all. You can hover in the air. For example, right now, I'm hovering in the air, sort of. There's me sitting on my chair, and I'm at an altitude of about 500 meters, because that's Canberra. It doesn't take me any energy to hover at 500 meters because I'm sitting on a chair that holds me up or just sitting on the ground that holds me up. Likewise, you could hover in midair, say suspended from cables or even suspended from a hot air balloon or something like that, and no energy is required. So clearly just staying in the air is a bit more complicated than some of the other things we've talked about. We know that staying in the air by being on top of a post or something takes no energy. Hot air balloons or dirigibles floating take no energy as well. So if you've got one of a kid's helium balloon at a fair, that will float away without batteries or any power source. On the other hand, we know that helicopters burn huge amounts of fuel. So it's a bit tricky here. We have to think about how we're staying in the air and why that particular thing requires energy. And that's what we're going to talk about in the next few videos.